Artificial intelligence is transforming nearly every industry, from healthcare and finance to manufacturing and scientific research. But behind every AI model, every chatbot response, and every image generated lies an enormous physical infrastructure consuming unprecedented amounts of electricity. Modern AI training clusters require tens of thousands of GPUs operating simultaneously, while inference workloads continue around the clock. As AI adoption accelerates worldwide, electricity demand from data centers is rising at a pace the industry has never experienced before. Analysts project that AI data centers could consume a significant share of global electricity within the coming decade. The digital revolution is no longer limited by computing power alone. It is increasingly constrained by the energy needed to keep these systems running. To meet this surge in demand, companies around the world are investing billions of dollars in new AI infrastructure. Entire campuses are being designed specifically for artificial intelligence, with buildings optimized for high-density computing, advanced networking, and sophisticated cooling systems. These facilities are far larger and far more power-intensive than traditional enterprise data centers. Instead of supporting thousands of users, they may serve millions of AI requests every day. The result is a global construction boom unlike anything the digital infrastructure industry has seen before. Every new AI data center represents not only more computing capacity, but also a dramatically greater demand for reliable, continuous electrical power. Ironically, the greatest challenge facing the AI industry today is not building faster processors, it is securing enough electricity. Across many regions, electrical grids are already operating near capacity, and connecting a new hyperscale AI campus can take years due to transmission upgrades, substation construction, and permitting requirements. Utilities are struggling to keep pace with the rapid growth in demand, forcing many projects to wait for infrastructure that does not yet exist. This creates a new bottleneck. Even if companies have the land, the capital, and the computing hardware, they may still be unable to operate because the electrical grid cannot deliver sufficient power. Solving this challenge requires rethinking how energy reaches the data center. One company believes the answer lies beyond the traditional electrical grid. EdgeCloudLink, better known as ECL, has developed a fundamentally different approach to powering AI infrastructure. Instead of relying exclusively on utility connections and diesel backup generators, ECL integrates hydrogen fuel cells, battery energy storage, advanced power electronics, and modular infrastructure into a unified energy system. Their goal is to deploy AI data centers more quickly while improving resilience and reducing dependence on conventional grid expansion. By treating energy generation as part of the data center itself, ECL is redefining the relationship between computing infrastructure and the power systems that support it. This vision became reality with ECL's operational hydrogen-powered AI data center in Mountain View, California. Rather than using hydrogen only as an emergency backup fuel, the facility demonstrates how hydrogen fuel cells can serve as a primary source of electrical power for AI computing. Hydrogen is stored on-site, converted into electricity through fuel cell modules, stabilized using battery energy storage, and distributed throughout the facility to power high-density computing systems. Water and low-grade heat are produced as byproducts instead of combustion emissions. While many companies continue waiting for larger grid connections, ECL has demonstrated an alternative model, one where hydrogen, rather than the electrical grid alone, becomes the foundation of next-generation AI infrastructure. In the next section, we'll follow that hydrogen journey from production to the moment it becomes electricity powering artificial intelligence. Every hydrogen-powered data center begins long before electricity reaches a server rack. It starts with hydrogen production. In the cleanest pathway, renewable electricity generated from solar panels, wind turbines, or other low-carbon energy sources powers electrolyzers. These machines split water molecules into hydrogen and oxygen using electricity. Oxygen is safely released or captured for industrial use, while hydrogen becomes a versatile energy carrier. Unlike batteries, which store electricity directly, hydrogen stores energy chemically, allowing it to be transported and used whenever power is needed. This ability to decouple energy production from energy consumption makes hydrogen especially attractive for large AI facilities that require continuous, reliable power around the clock. Once produced, the hydrogen must be delivered safely to the data center. Depending on location and infrastructure, hydrogen can arrive through dedicated pipelines or be transported in high-pressure tube trailers. For many early hydrogen projects, truck delivery provides the flexibility to deploy facilities without waiting for extensive pipeline networks. Upon arrival, operators connect the delivery system to secure transfer stations equipped with pressure regulators, isolation valves, leak detection systems, and automated safety controls. Every transfer is carefully monitored to ensure safe handling of the gas. At this stage, hydrogen has completed the first part of its journey. It has moved from a production facility to the data center, ready to become the primary energy source that will eventually power thousands of AI processors. After delivery, hydrogen is transferred into specially designed on-site storage vessels. These tanks are engineered to safely contain hydrogen at high pressures while maintaining strict operational and safety standards. Sensors continuously monitor pressure, temperature, and flow conditions, allowing operators to detect even minor changes in system performance. Redundant valves and emergency shutdown systems further enhance operational reliability. Unlike diesel fuel storage, hydrogen storage integrates directly into the energy architecture of the data center, creating a continuous supply that feeds the power generation system. The stored hydrogen acts as an energy reservoir, ensuring that fuel is available whenever computing demand requires additional electrical power. The heart of ECL's energy system is the hydrogen fuel cell. Instead of burning hydrogen through combustion, fuel cells generate electricity through an electrochemical reaction. Hydrogen enters the fuel cell stack at the anode, where it separates into protons and electrons. The electrons travel through an external electrical circuit, producing usable electricity, while the protons move through a specialized membrane before combining with oxygen at the cathode. This process produces water and low-grade heat as natural byproducts rather than carbon emissions. Because there is no combustion, fuel cells operate quietly, efficiently, and with fewer moving parts than conventional generators. Multiple modular fuel cell units can operate together, allowing capacity to scale alongside the growing power requirements of AI infrastructure. Generating electricity is only part of the process. The electrical output from the fuel cells must be conditioned and integrated into the data center's power architecture before it can support sensitive computing equipment. Battery energy storage systems smooth short-term fluctuations, while power conversion equipment stabilizes voltage and frequency to ensure consistent electrical quality. From there, electricity flows into the medium voltage distribution system, where it begins its journey toward thousands of AI processors. Along the way, the hydrogen fuel cells continue producing clean electricity while simultaneously generating water and recoverable heat, improving overall system efficiency. At this point, hydrogen has completed its transformation from a stored fuel into a dependable electrical supply. In the next section, we will follow that electricity as it moves through batteries, switchgear, power distribution equipment, and finally into the high-density AI servers performing the computational work. Before electricity reaches the computing equipment, it first passes through a battery energy storage system, or BESS. While hydrogen fuel cells provide continuous base load power, batteries respond almost instantly to sudden changes in AI workloads. These rapid fluctuations are common in modern GPU clusters. The battery system absorbs these spikes, stabilizes the electrical supply, and provides uninterrupted power during equipment transitions. Hydrogen delivers long-duration energy, while batteries provide instant response, creating a resilient hybrid power architecture for mission-critical AI operations. Once stabilized, electricity flows into the medium-voltage switchgear, the central traffic controller of the electrical system. It intelligently routes power from hydrogen fuel cells, batteries, and, where available, the utility grid throughout the facility. Advanced protection systems continuously monitor electrical conditions and isolate faults before they can affect the entire campus. Reliable power distribution begins here. Electricity now reaches the computing halls where thousands of GPUs perform AI training, inference, and scientific computing. Individual racks may consume well over 100 kilowatts, requiring precision electrical engineering. Every cable, busway, connector, and power supply has been designed to deliver clean, uninterrupted electricity. This is where the stored energy inside hydrogen is ultimately transformed into artificial intelligence. Before reaching each server rack, electricity passes through power distribution units, or PDUs. These systems provide the final stage of voltage conditioning, load balancing, and rack-level monitoring. Operators can observe power quality and energy consumption in real time while ensuring every AI rack receives precisely the electrical supply it requires. With stable electricity delivered, the GPUs begin performing trillions of calculations every second. But every watt consumed becomes heat. At these power densities, cooling becomes equally as important as electricity. Without advanced thermal management, these processors would rapidly overheat. The next stage of the story follows the heat instead of the electricity. Modern AI processors generate extraordinary amounts of heat. Instead of relying on air cooling, coolant flows directly through cold plates attached to CPUs and GPUs, removing heat far more efficiently. This enables higher computing densities while reducing cooling energy and improving performance. The heated coolant travels to the cooling plant where pumps, heat exchangers, chillers, and cooling towers remove the heat before sending the coolant back to the servers. Every watt consumed by AI eventually becomes heat that must be continuously removed to maintain reliable operation. Thousands of sensors monitor hydrogen pressure, fuel cell performance, battery status, electrical loads, coolant temperatures, and server utilization. Intelligent control systems automatically optimize every subsystem, creating one coordinated energy ecosystem capable of operating around the clock. Mission-critical AI infrastructure demands redundancy. Multiple hydrogen storage tanks, modular fuel cells, redundant cooling equipment, battery systems, and intelligent monitoring ensure uninterrupted operation. Reliability is not achieved through one machine. It is engineered into every layer of the system. Together, hydrogen production, storage, fuel cells, batteries, switchgear, cooling, and digital controls create a new model for powering AI. Instead of depending entirely on expanding electrical grids, ECL integrates energy generation directly into the data center itself, demonstrating an alternative architecture for future AI infrastructure. One hydrogen-powered AI data center is only the beginning. ECL's modular approach allows additional hydrogen fuel cells, batteries, cooling systems, and electrical infrastructure to be added as demand grows. This enables facilities to expand from a few megawatts to tens of megawatts while maintaining the same underlying engineering architecture. ECL's long-term vision extends to hydrogen-powered AI campuses capable of reaching 1 gigawatt of electrical capacity. A project of this scale requires a fully integrated ecosystem of hydrogen storage, fuel cells, batteries, cooling, and electrical distribution, working together to power some of the world's largest AI clusters. Looking at the complete system, renewable electricity produces hydrogen through electrolysis. Hydrogen is transported, stored, and converted into electricity by fuel cells. Battery storage stabilizes the output before switchgear, and PDUs deliver power to AI servers. Cooling systems remove heat, while digital monitoring continuously optimizes every stage. Hydrogen is transformed into computation through one continuous engineering process. The rapid growth of artificial intelligence requires new ways of thinking about energy. Hydrogen-powered data centers demonstrate that computing infrastructure and energy infrastructure can be designed together. While this approach will not replace every conventional data center, it offers a compelling option where reliable grid capacity is limited or deployment speed is critical. The story of ECL is ultimately about much more than one company. It represents a new way of connecting energy systems with digital infrastructure. Every AI response depends on hidden networks of power generation, electrical distribution, cooling, automation, and control. Hydrogen adds another powerful option to that engineering toolbox. Whether it becomes a mainstream solution will depend on continued advances in hydrogen production, fuel cells, infrastructure, economics, and operational performance. But one lesson is already clear: the future of artificial intelligence will be shaped not only by faster chips, but also by smarter energy systems. Understanding those hidden systems helps us better understand the technologies that will define the decades ahead. Thank you for watching. If you enjoy exploring the hidden engineering systems that power our world, subscribe to Renewable Energy for more in-depth engineering documentaries, and visit H2 Hub by Renewable Energy to continue exploring the technologies shaping the future of clean energy and artificial intelligence.